One of the earliest networks to use a random access strategy is ALOHA net. As you may guess, this was a network in Hawaii, and in a setting where they could not easily run wires between the different nodes on the network, either because there were mountains in the way or oceans in the way, and instead they had to broadcast wirelessly. And so you have the shared medium and the broadcast problems to deal with. In ALOHA net, a node that's say blue here would start broadcasting, and it would keep broadcasting as long as it had some data to send, up to a certain length of data at least. Along the way, it would watch and see whether the chunk of data it just sent conflicted with anyone else or not. And if it did, then it would consider that attempt to send a failure for that little chunk of the message, for a defined chunk size here. It would wait a certain amount of time, a certain number of slots. It would wait one slot or not wait one slot with probability p, so it becomes less and less likely that you wait a long time, but still some probability that you wait 2 or 3 times. Because of these random delays, when a bunch of nodes are trying to talk, if they collide with each other, then you might have some empty airtime when everyone is just waiting a little bit longer to make sure there's no conflict. So here we see that the green node decided not to wait. It decided to retry again, and it got its message A2 out. Whereas both red and purple ended up trying to wait past 2 slots, and then when they restarted, they conflicted again. But then purple decided to try right away and succeeded, whereas red is still waiting. So you can see how this works and how generally it allows negotiation of the shared channel. It's not unlike what you would do at the dinner table. 2 people might start talking and then one of them decides to go ahead while one of them waits, or they might decide to wait and there's an awkward pause, and so on. The picture I've drawn here is actually slotted ALOHA because I am drawing it with these slots. It has some good properties, which is if only blue needs to talk and no one else has any data to send, then blue ends up with the whole bandwidth. It's able to stream out its information at each of these slots. It detects that there was no collision, and so it keeps sending out data. If there are multiple nodes that want to talk, like red, green, and purple here, it's fair in the sense that everyone gets an equal opportunity as long as they're all playing by the rules of waiting a random amount of time. Sometimes your random pauses will be short and sometimes they will be long, but the same as everyone else, and everyone has equal opportunity to attempt to send some data. The drawbacks here are that when you do collide, you've wasted that time slot, or when everyone is waiting, then that time slot is also wasted. And if you work through the numbers here, it turns out that you only end up with about 37% of the bandwidth. The original ALOHA net was actually unslotted. That is, there would not be regular starting points where everyone would check and synchronize. That ends up cutting your utilization by half again, so only something like 18%. And that should intuitively make sense because if I move around A1 here relative to B3, then that increases the chance that they overlap compared to always starting on the same boundary.